Now we are taking into considerations of the Amdalh laws. This law deals with the potential speedup of a program using multiple processors compared to a single one. Actually, this law applies for many other fields like business, economicals, industrial engineering, not just computing. Let T be the total execution time of the program using a single processor. Then the speedup using a parallel processor with N processor that fully exploit the parallel portions of the programs is as follows. Speedup equal to the time to execute a program on a single processor over the time to execute programs on N parallel processor. And here we have the final formula. I give you 1 minute to think about F here. You already know N, the numbers of the parallel processor, or the amounts of enhancement that you make on the system. Now the question is, what is F? I give you 1 minute to think about this factor. I hope that you already find the result. Now, this is my rationale. Take a look at the program. This is my program, for example. This program has F is the part of the program that can exploit the multi-core of the processor. That means F is the part of the programs that can be executed parallelly. So 1 minus F is the left part, which is the part of the programs that can only be executed sequentially. Suppose you have a program with 1000 instructions. But when you move that programs from a single core system to a multi-cores, only some parts of 1000 instructions can be executed parallelly. And that part is the F part of this formula. Now, there are two conclusions that we can withdraw from these formulas. First, if F is small or very small, then the multi-core is useless. The second conclusion is that when n tends to infinite, the speedup is multiplied 1 over 1 minus f. So there are diminishing return for using more processor. More core is not always the best. You will not always benefit from increasing the number of core of the processor. Now we will do some exercise. The first one considers the following two enhancements in a system. There are two circumstances. The first one is you make a speedup of 20 times on 10% of times of the systems. And the second circumstance is you make the speedup of 1.6 on 80% of times of the systems. I give you 1 minute to think about the problems. This is my solutions. I just want to visualize the circumstances of the problems. For the first circumstances, this is the lines that represent the times of the whole systems. And for the first circumstances, you make a speed up 20 times on 10% of the times. Yes, here I will. This is 20 times. You make an abrupt enhancement on the system, right? And for the second circumstances, we have the same lines, and in these circumstances, you make an enhancement only 1.6 times in comparison to the normal conditions. Now you need to calculate the speed up of individual circumstances. Okay, so for the first one, we have F equal to 10%. That means 0.1. And N is the enhancement in this case is 20. So the speed up in these circumstances equal to 1 over 1 minus F equal to 0.9 plus 0.1 over 20. Right? And this equal to 1.105. This is the speed up. Now for the second circumstances, we have F equal to 80%. That means 0.8. N equal to 1.6. Now the speed up is 1 over 0.2 plus 0.8 over 1.6. And this equal to 1.43. So for the second circumstances, you can see that the speed up is better than the first one. We can also withdraw another conclusions from this exercise. You can see that for the second circumstances, the levels of improvements is not much, but you make on a large part of the system. While for the first circumstances, the enhancement is very large, but you made on only a small part of the times of the whole system. And you can see that the second circumstances give a better speed up, which is, I can say that make common case was is always the best. It's much better than you focus on a small part of the system. Now, we move to the second exercise. Consider the following processor which is clocked at 2 GHz. There is a program that run on this processor, and the programs consist of 4 instruction types. These are add, integer, range, load, and store. And this is a percentage of time that each instructions contribute to the whole programs. And this is the cycle per instructions of each instruction type. Now, let's take a look at the speed up levels for the following possible improvements. The first improvement is that you make change to the CPIs of the branch instructions from 4 to 3 to make it faster. For the second case, you increase the clock frequencies of the CPUs. That means to push the CPU to work faster. And for the third case, you make the CPU run faster only for the store instructions by decrease the cycle per instructions from 3 to 2. Please make some calculations to withdraw which one is the best improvement in these three cases. I give you 1 minute to think about this. This is my solutions. For the first circumstances, we change the CPI from 4 to 3. F in this case is 20% equal to 0.32 and equal to 4 over 3, which is equal to 1.333. So we use the speed up in this case is 1 over 0.8 and 0.2 over 1.333, and this equal to 1.05. For the second improvement, we have F equal to 1 and equal to 2.3 over 2. So the speed up is 1 over 0 plus 1 over 1.15. This equal to 1.15. And for the third improvement, because this is 10% and equal to 3 over 2 equal to 1.5. 0.9 plus 0.1 over 0.34. So the best case is the second one. That is you increase the clock frequency. When you increase the clock's frequency, not only the CPU run fast, but the whole system will run fast. And this aligns with the principle that we withdraw from our last example. That means make common case fast. The solution, the answer to this, and the answer to the exercise is that maybe you don't need to do the calculations. You just look at the input, right? And you can guess the output, because the increase of the clock frequency will affect the whole system. So this improvement should be the best. And the calculations confirm that guess. Okay, so that's conclude our sections about the Amdalh law, and it also concludes the first chapters about evolutions and performance.